Alright, so in this video we are going to go over the second part of section 2.3, the derivative. And well, on the first part of this video we went over how to find derivatives of functions using the limit definition. By the way, if you're reading the textbook and maybe the homework might ask you to use what they call the three-step process or the three-step method to find the derivative. Well, if you look at all the work that we did, it's not really three steps. What I mean, I don't usually call it like the three-step method. I just call it the limit definition because, well, it involves finding a limit. Now, so we're gonna learn a shorter way to find derivatives, and well, so we're gonna go over the differentiation rules. So all we have to do when we have a function of the form um, x to the n, so what we do in this case is, um, oops, didn't mean to do that. It's actually x to the n. That's the general power rule. All we do is multiply by the old exponent, by the original exponent, and subtract 1 to the exponent. For example, let me do stuff on the side like if I have x to the 7, the derivative will be 7 times x to the 7 minus 1, which is 7x to the 6th power. If I have the same rule applies when I have um, the the same x to the n function but multiplied by another number. For example, 5x to the 6th, the derivative will be 6 times 5, x to the 6 minus 1, which equals 30, x to the 6 minus 1, which is 5. So see how short it is now. So let's go back to that first example. So using these differentiation rules, f prime of x equals 3 times 2 x to the 3 minus 1 minus 7x to the 1 minus 1, which is 6x squared minus, well, x to the 1 minus 1 is going to be x to the 0, and any quantity to the 0 is simply 1. 1 times 7 is 7. It's the same answer that we got over here. And it didn't take, what, like 7-8 minutes to complete. No, we did it in a couple of seconds. All right, another quick rule that I would like to I didn't add it here. For example, when you have cx, the derivative is c. For example, 5x, the derivative is 5. The derivative of 7x is 7. The derivative of 9x is 9, etc. All right. Now about notation, ways to denote the derivative of. Notice I have been using the prime notation, but we also have this d dx, d over dx. So the derivative, let me write it down, notation, so f prime of x is the same as saying dy dx. It's similar to delta y over delta x, or sometimes df dx, and also we use y prime. I'm going to use the ones that I'm going to use the most are the following. The y prime, that's the one, that's not the one I prefer because I think it's the one that takes less writing, but it's also good to put names to this notation. The one that involves the ratio dy to dx, this is Leibniz notation. After the mathematician Leibniz, and this one is the prime notation is the Lagrangian notation. All right, it's after the another mathematician of last name Lagrange. All right, But I'm going to use the y prime. All right, so let's do one example. Let's do a few examples. So, okay, so y prime equals 3 times 3 minus 1 minus 2 times 6x to the 2 minus 1 plus 5x to the 1 minus 1 plus the derivative, by the way, the derivative of a constant, the derivative of a number is 0. I didn't write that rule, by the way. Let me write it down here. The derivative with respect x of a constant c equals to 0. And in this case, well, no need to write down the 0. Well, I'm going to write it down just because. Well, let's simplify this. So that's going to be 3x squared minus 12x to the first plus 5x to the 1 minus 1, which is 0, and this is simply 5. All right. So after some practice, guys, you won't need to write this 3 minus 1, and you don't need to share the multiplication times 2. All you can do is simply go straight to okay, do that on your head, because in some cases these are easy numbers to deal with. So 3x to the 3 minus 1, which is 2, 6 times 2, which is 12, and the derivative of 5x, which is just 5. All right, so no need to show all these operations I did. I just did it for this first example just to show you how the general power rule works. All right, in some cases like letter B and on, we may need to do some algebraic rewrites before we can take a derivative, because in this case, this x and x cubed right here are in the denominator, and in this case we cannot differentiate those two functions while they are in the denominator. So let's rewrite this as 4 x to the negative 1 minus 6 x to the negative 3. So now that we have those two functions rewritten, we're good to go and find the derivative y prime, which is, well, 4 times negative 1, that's a negative 4 x to the negative 1 minus 1, which is negative 2. And then be careful here, because this negative 3 power times this negative 6 will become positive 6 times 3, which is 18. X to the negative 3 minus 1, that's going to give us a negative 4. All right, we subtract 1 to the exponent to get that new exponent. Now, we are essentially done with the calculus part of the problem. However, we need to clear this negative exponent. So let's rewrite this as 4 over x squared plus 18 over x to the fourth. And this is final answer. For letter C, we're going to do basically the same. Well, we need to rewrite because we don't have we cannot just differentiate the radicals this way. We need to rewrite this the following way. So we would have to write this radical as x to the 1/2 first minus 5 over x to the 2/3. And then we're going to move this x to the 2/3 to the numerator with negative exponent for the same reason as for letter B. Notice we weren't able to differentiate while we had these terms in the denominator. So let's move it up to the numerator. Okay, so this is not the calculus yet. This is only the algebra that we need to rewrite the function. So now let's do the calculus. Y prime 1/2 x to the, I'm going to do the numbers here, 1/2 minus 1, and then minus negative 2/3 times 5 x to the negative 2/3 minus 1. All right. We need the addition, well, in this case, subtraction with fractions in order to get the derivative for this. Well, 1/2 minus 1, that's basically that's the same as saying 1/2 minus 2/2. And when we do that, we get, okay, well, that's 1/2 x to the negative 1/2. And then for negative to negative, that's a positive 2/3. Or actually, if we multiply this, 2/3 times 5, that's going to give us 10/3. X to the negative 2/3 minus 1, but combining negative 2/3 minus 1 is the same as combining negative 2/3 with negative 3/3, right? Negative 2/3 minus 1 is, so that's going to give us negative to the, so negative 5/3. And we're done with the calculus, except that we still need to rewrite this in positive exponent and also go back to rewrite it as a radical. So we're going to do 2x to the 1/2 in the denominator of the first term plus 10 over 3x to the 5/3. And we are almost there. All we do is write 1 over 2 square root of x plus 10 over 3 cube root of x to the 5th power. And that's final answer. All right. Okay, let me see if I can write it a little bit better. Oops. All right. Let's do another example. Letter D, y equals x minus 6 times 4x minus 9. Well, I know what you might be thinking, maybe because, well, here we have the product of two functions. Maybe we find the derivative of the first factor, which is 1, times the derivative of the second factor, which is 4. Final answer is 4. Be careful here. In this case, that's not how we do. Later in the semester, we're going to look at the product and the quotient rules and the chain rule and other rules to differentiate functions. However, for now, what we're going to do is FOIL to get 4x squared minus 9x minus 24x plus 54. All right, let's keep combining like terms, in particular these two, 9x and 24x, and that's going to give us that's 33x. All right, 4x squared minus 33x plus 54. Oh wait, no, that's not final answer, that's just the foiling. So now we're ready to take the derivative y prime. The derivative, that's 2 times 4, which is going to be 8x minus 33. All right, and that 33, where is that coming from? Well, from that rule I mentioned before, like cx, it's just c, like 3x, the derivative is 3, 5x equals 3, the derivative of 10x equals to 10, and so on and so forth. All right, that's final answer here. All right, so for the next example, letter E, square root of x times the polynomial 3x squared minus 4x plus 3. All right, again, so this one is going to take a few steps before we can even take the derivative of this function. Number one, let's write this radical as x to the 1/2 times 3x squared minus 4x plus 3. And well, what are we going to do? We are going to distribute. Oops, that didn't right, yeah. We're going to distribute. And well, what are we going to get here? So when we multiply x to the 1/2, x to the 1/2 times x squared, well, of course, I'm going to leave the coefficient 3. So x to the 1/2 plus 2, so that's going to give us a 5/2. All right. Where am I getting these 5/2 from? Because when we multiply the bases, the same base, what do we do with the exponents? We add the exponents. So what we do is add 1/2 plus 2. That should give us 5/2. And then I'm going to multiply x to the 1/2 times x. And that's going to give us minus 4x to the 3/2. And then plus 3x to the 1/2. And here we're ready to do the calculus, to use the general power rule. Y prime equals to, okay, this 5/2 multiplies with the 3, this 3/4 multiply, 3/2 multiply with the 4, and this 1/2 multiplies with the 3. So that's what's going to happen there. All right, so 3 times 5/2, that's a 15/2, x to the 5/2 minus 1, which is 2/2, that's a 3/2. 4 times 3, which is 12, over 2, which will reduce to 2 and then into 6 in the next step. And 3/2 minus 1, which is 2/2, that's going to leave us with 1/2. And then 3 times 1/2, that's going to be plus, well, it's actually minus over here, not plus. And then this one is plus 3/2 of x to the 1/2 minus 1, which is negative 1/2. And let's rewrite this as radicals with positive exponents. And well, so this will be 15 halves of the square root of x cubed minus 6 square root of x. And recall then in a previous example, in particular, it was letter C, we went to get from x to the negative 1/2 all the way to radical x in the denominator, the square root of x in the denominator, that is 3 over 2 square root of x. Final answer. All right. Let's see. Let's move on to the next example, letter F. For letter F, yes, we have a quotient of two functions. Yes, later in the semester, we're going to learn how to work with the quotient rule to take derivatives. Even after knowing that quotient rule would be like overkill to do, it would be better to do what we are about to do. And in this case, well, notice that we have an expression that has the following form. We have an expression of the form a plus b over c, which can be split into a over c plus b over c. We're going to do that for this expression right here, 6x to the 7th over x to the 4th minus 7x cubed over x to the 4th. What is this going to give us? Well, so recall the quotient rule for exponents. Recall when we have a to the m divided by a to the n. This is a to the m minus n. A to the m minus n, in this case, 7 minus 4, 3 minus 4. That's what we're going to do here. So 6x to the 7 minus 4, which is 3, minus 7 x to the 3 minus 4, which is negative 1. Now, let's do y prime. Let's do the derivative. And again, 6 times 3, negative 1 times 7. That's an 18. x squared. 3 minus 1, negative 1 minus 1, be careful, x minus 2, and also negative 1 times negative 7 is going to be positive 7. Alright, positive 7, and we are essentially done with the calculus. We're good to go and move on. Just clean up the negative exponents. That's going to give us 18x squared plus 7 over x squared. Alright, final answer for this one, by the way. Is that what we should have obtained? Yes. Alright. Okay, so yes, I was comparing with my notes and I think I did a mistake on my notes, but not here in the video. All right, so of course there's many presentations of these kinds of examples, but as in a matter of a summary, well, be be sure to keep in mind the properties of radicals, the laws of exponents, etc. Let's do another application. Well, it's not an application to like physics or something like that. So we are going to use the general power rules to find slopes. Yes, we already did something like this in the previous example. However, in the previous example, I mean not in the previous example, in the previous section, we used the limit definition to find the derivative. Remember that long process? So no, we're not going to do that anymore. And well, we're going to use the derivative because, again, the derivative means the slope of the tangent line at a given point. So we have this function right here, f of x equals to 8x minus x squared. And they're asking us to find the slope of the tangent line at x equals to 2. So when x equals to 2, we have this point right here, and over there we can see this tangent line. All right, it's whoops, let me make this better. Yes, all right. And well, of course, here we have all the results already. Yes, in this particular example, this is what we should get: y equals 4x plus 4. And well, let's find the slope of the tangent line at x equals to 2. So in order to find the slope of the tangent, we do the derivative. If they were asking us to find the slope of the secant line, then we would need two different points, which is what we did in the previous section. But now we want the tangent line. For that, let's take the derivative, f of x, f prime of x, which is 8 minus 2x. And now the way that we are interpret this derivative, yes, of course, over here in the previous examples, we did a lot of algebra, we took derivatives, yes, and we obtained functions. But what do these functions represent? Well, for example, for letter A, this derivative represents the slope of the tangent line at any point on the graph of y equals x cubed minus 6x squared plus 5x plus 2, and in this case for any real number. It's a polynomial. It's defined for all real numbers, that is, the derivative exists or is defined for every value of x. And then this derivative right here represents the slope of the tangent line at any point of the function y equals 4 over x minus 6 over x cubed, except at x equals to 0. We cannot find the derivative at x equals to 0 because if you look at this function, if you look at this form, see how does we have it, it's not defined at x equals to 0. We have restricted values at x equals 0, and so on and so forth. That's what all these derivatives mean. So now that we found the derivative of 8x minus x squared, we can find the derivative at x equals to 2. Oops. Which is 8 minus 4, which equals to 4. So that is the slope. Again, let's recall that derivative means slope. Derivative means slope. And well, let's find the equation of the line at x equals to 2. Of course, what do we need to know in order to find the equation of the line? Well, we need a point and the slope. So we got the slope. We got the slope right here, which is this value is 4. Now we need a point. What's the point? Well, of course, they're giving us the point over here, 2, 12. But sometimes they're not going to give us that point on the instructions of the problem, or they're not going to give us the graph of the function. So if that were the case, all you need to do here is find f of 2 to find the y value corresponding to the x value of 2. So that's an 8 times 2 minus 2 squared. That's an 8 times 2, which is 16 minus 4, which equals to 12. And yes, indeed, it coincides with what we have over here. All right, is this point. So the point, which is 2, 12, and the slope, which is m equals to 4. We're going to use the point slope form, which, by the way, the point slope form, y minus y1 equals m times x minus x1, where y minus y1, that's a 12, equals m, which is 4, times x minus x1, which is 2. All right, and let me change this to blue. And in this case, well, we're essentially done with this problem. I mean, all we have to do is distribute. This is just like any intermediate algebra problem in which you find the slope and the point to come up with the equation of the line. That's for x minus 8, and then just add 12 to both sides to isolate the y to get y by itself, and this will be y equals 4x 12 minus 8, that's a plus 4. And yes, it's the same result that we got over here from the graph. And of course, so again, what is the power of finding the derivative of function? So this derivative right here, this derivative f of x equals to 8 minus 2x is going to be useful to find the slope of the tangent line at any particular value of x. For example, in this case, we did it for x equals to 2, all right? However, you can use the same derivative to find the slope at, I don't know, maybe at x equals to 6, the slope at x equals to 7, at x equals to 1, perhaps, I don't know, at 5, at any point that you want, at 8, at 4, any of your favorite points. And that's what you are going to do on the homework, all right? And well, this is the last example for this section. I believe this is a good place to quit. I'll see you on the next section.